Hey students, this is your Professor Omelianchuk, and today I want to talk about strategizing subderivations and deriving logical truth. So I'm going to talk about the strategy of conditional proof, the strategy of reductio ad absurdum, and then how to do some derivations that don't have any premises. Right? So as you probably have already figured out, right, the big question always with these types of problems is, how do I know what to assume? Right? And that's a big question. I understand that question. And one of the reasons why I chose this textbook is because it uses only two rules that require that you make assumptions. And those two rules correspond with the two main strategies that are involved when doing derivations, right? And so that's really kind of a nice system. This is why I like it. And so let's talk about those, all right? Let's talk about the first strategy called conditional proof, right? What is the strategy of conditional proof? Well, you'll deploy this strategy if your target is a conditional, right? So suppose you have to derive a conditional and you have to create one. You have to use arrow introduction to get it. Okay, then your strategy for getting your target involves conditional proof. And just what that means is that you always begin with the assumption of the antecedent of the conditional. So what you're assuming, right, the answer to your question, how do I know what to assume when I have to derive a conditional? Well, you always assume the antecedent of that conditional, right? And then you try to work out whatever that consequent is of that conditional in the subderivation, right? So if your target is AA, arrow not BA, then you assume AA, right? And then you try to deduce not BA and stay in the scope of the subderivation. Okay, that's all conditional proof means. And that's what we've been doing just in the last assignments, right? And in the last lectures, it's just we haven't given this formal name. Right, reductio ad absurdum, we've talked about this, right? This is an argument strategy that seeks to prove a claim by showing that the denial of the claim leads to an absurdity or entails an absurdity, okay? So this corresponds to the rule of negation introduction. If your target is a negation or you are completely stuck, right, then the strategy for getting your target likely involves using reductio ad absurdum, okay, which is going to be negation introduction. Right, I would use this as a last resort. Okay, the temptation, especially for students who are very new at this, because they often, in some ways this is bad advice because you often feel stuck a lot, right? Try this last resort, okay? Because this is a hard rule to use. It's a hard strategy to deploy, but it does work. All right, it does work, and it can get you unstuck. Okay, basically, what though you have to remember is that what you assume, the answer to the how do I know what to assume question, will always be the opposite of what you're trying to derive. So suppose your target is FA, okay, then you would assume not FA, right, and then try to get a contradiction, and then stay within the scope, okay, of the assumption. So that's basically it for the names of the strategies, right? The big difference is that in conditional proof, you really like your assumption. You're wanting to connect it with something else. You want to show that it entails something that's desirable, okay? And that will then create an arrow, right? An if-then statement, right? In reductio ad absurdum, you don't like your assumption. What you want to do is show that it leads to a contradiction and therefore it deserves to be negated, okay? All right, so here's kind of a tough problem, right? Let's go over this and just think about this, right? Let's think about, okay, all right, how are we going to approach this thing, right? Our target is EA, right? So that's going to be where we want to go. And you see that there's an EA available to us, all right, and a consequent of a conditional on line 2 that is embedded in a larger conjunction. So you might think, oh, wow, that's nice. Okay, maybe if I can get not GA by itself, then I could use arrow elimination on the last line. Okay, but then where are you going to get not GA from? All right, and then this old familiar problem, oh no, not GA is inside of a disjunction, right? You can bet when you see this kind of pattern, right, when you have, right, the antecedent of a conditional in a conjunction that's leading to what you want, disjunction elimination is going to be the rule you're going to use in your last line, because notice the pattern. Here's the disjunction, right? P or Q, and this is going to be the Q or R formula, and R is going to be what we want to derive in our last line. So that tells us this is going to be used in our last line. Okay, so what that means then is that we have to get these three requirements. Now we have two of them that we can eliminate for fairly easily. We can do arrow elimination with lines 1 and 3 and get the disjunction. We can do conjunction elimination and get this part. But we're going to have to create the Q arrow R pattern, which would say not HA, arrow EA. Okay, so that one we're going to have to create. Okay, that one's the one we're going to have to create. Okay. Okay, so there's the Q, right? And that's why I highlight the not HA there. And you might be wondering, okay, how are we going to get that, right? How's that going to work? And what I want to draw your attention to is the second conjunct there on line 2 that I have underlined in yellow, right? The reason I highlight this is because there's a special relationship between this conditional here and the conditional that we want to get as a subtarget for the requirements of our rule that we're going to use in our last line. Now, what's that relationship? Answer: relationship is contraposition. Now, that's a fancy word, but all it is just an equivalence relation. And here it is. So you have a formula P arrow Q that's logically equivalent with not Q, not P, right? Not Q, arrow, not P. Not Q, arrow, not P. I had to say that a couple times to make sure I was saying it right. Sorry about that. Okay, so here's what I want you to notice, okay, in our problem, right? So this is what we have in the conjunction right here, not EA, arrow, HA, and that's logically equivalent with this, not HA, arrow, not EA. Or more simply, not HA, arrow, EA, which is exactly one of the subtargets that we want to get. So we're going to make use of that conjunction, right? That's going to come in handy for us. All right, so here's the problem fully laid out. Disjunction elimination is what we're going to use on our last line. So let's get the two parts that we can get easily with elimination rules. Okay, we're going to use arrow elimination from 1 and 3 to get the disjunction, conjunction elimination on line 2 to get that first conditional. Now I need to create this conditional. So what I'm going to do is assume for conditional proof not HA, because that is what the arrow introduction rule requires me to do. You want to get this conditional here? Well, then assume P. All right, I want to get this conditional here, so assume not HA. All right, now what do I do? Okay, so how am I going to get EA, right? Isn't that what I was trying to get all along, right? And this is one of the things about derivations that are just, it's so disgustingly annoying, is that you're trying to work out your target in a subderivation. And that's what you're trying to get ultimately. So, haven't we just kind of gotten ourselves committed into something here that's kind of silly that we can't get out of? And how do we do? We seem to be completely stuck, all right? So negation introduction might be a good thing to try at this point, okay? So what negation introduction tells me to do is to assume the very opposite of my target, which is not EA, right? Not EA. That's the very opposite of my target. So I got to start another subderivation, so I indent a little bit more to the left, okay? And I note to myself that I'm assuming that for negation intro, right? I'm assuming that for reductio. Up here, I assume this for conditional proof, right? So this is, again, my notation here corresponds to the name of the strategies that I'm invoking. Okay, so now that I've assumed this, I am now committed to deriving a contradiction. So now I need to inspect my assumptions and my premises and see if I can derive a contradiction. And guess what? I already see two elements of that contradiction. Here they are, right? They're in line 2 and line 6, right? So I need to get those two things together, okay? Now, in order to get this HA, what I need is not EA, okay? And I have not EA as an assumption on line 7, right? So what I'm going to do is I'm actually going to eliminate this disjunction and bring this, eliminate this conjunction and bring this conjunct down into the subderivation that I'm working on. All right, so I continue the one that I started already on line 6, right? And then I continue the one I started on line 7. Okay, now I got that conditional. Now I can do arrow elimination and get HA, right? And I can now combine the assumption I made on line 6 on line 9, in the formula on line 9, and create my contradiction using conjunction introduction, right? Okay, so now I've derived a contradiction. I've satisfied the requirements of this rule, so I can discharge this subderivation, which is what I'm going to do. And I'm going to negate the assumption that I had assumed for reductio, right? So I have to use negation introduction. So I'm going to put a negation on that assumption and write on line 11, not EA. Now that's going to come through lines 7 through 10 because that is the whole subderivation that justifies that move. Now I am within the scope of this subderivation, and what I had done there originally is assumed not HA for a conditional proof. All right, so I assumed that for conditional proof, and that's exactly what I wanted, right? I wanted to get this. Now I do have a double negation here, so I need to get rid of those, right? So let's get rid of those using negation elimination. Okay, now I got what I wanted. Now I got EA, okay? Now my proof isn't done, okay? I actually have to discharge the subderivation before I'm done. And I'm going to write on line 13, not HA arrow EA. Right, and that's going to be justified by lines 6 through 12. That's going to be the subderivation, right? That is arrow introduction. And so now I got all three of my things, all right? On lines 4, 5, and 13, I have those three things. That justifies the elimination of the disjunction, and I can write EA, right? So I'm done, right? So that's a good illustration of a pretty intermediately difficult problem. Believe me, these things can get way harder than you realize. Okay, and so the point though of this sort of problem is to give you a sense of how these three rules interact, and they often do because you have to do creating conditionals. Sometimes you got to use reductio to get what you want, to get a conditional. All right, and so I like this problem because it sort of illustrates both of the conditional proof and reductio ad absurdum strategies in order to satisfy this rule. Okay? Let's talk about deriving logical truths. Okay, remember that logical truths cannot be false. Right? So that also means that they need no premises in order to be true. They don't depend on other things being true to be true. They just are true all by themselves. Right? So that means then that we should be able to derive them without premises. Okay, so we want to be able to do this, and our system of derivation does allow this. Okay, we have a good system that allows us to do this. Right? So think of the logical truth FA arrow FA. That one's really easy to derive. I don't need any premises to do that. But what do I do? Well, let's think about what the main connective of this is. It's an arrow. So what I'm going to do then on my last line is use arrow introduction. So what do I assume? Well, I assume for conditional proof FA. I always assume the antecedent of the conditional I want to derive. Then, within the scope of that subderivation, I need to derive FA from itself, which is really easy. I use the little repetition rule from line 1. And then from lines 1 through 2, right, I stop the subderivation, I discharge it, and I write FA arrow FA. Okay? All right. Here's something you should know, at least when we're talking about derivation, right? Logical truths are called theorems, right? So what is a theorem in derivation speak, right? A theorem is a derivation of a logical truth. And what's special about it is that it has no premises, okay? So a theorem in derivation speak, right, is a logical truth, okay? It's a derivation of a logical truth, meaning that it's a derivation that has no premises. So let's look at contraposition, right? We talked about that earlier. And is there a way that we can derive contraposition? So this might be a little complicated, I realize, all right? But I just ask you to kind of stick with it here, okay? Actually, I don't think this one's too complicated now that I think of it. Okay. So notice that, all right, so this is contraposition, right? So this is at least one side of it. It's not an equivalence relationship, but it does work. Right? If this is true, then certainly this is true. All right, and if you did a truth table, you get nothing but T's under the main connective. Of course, the main connective is an arrow, right? So I need to derive this. All right, so what do I assume? Well, we're going to deploy the strategy of conditional proof. right? And so what I should do then, right, is assume the antecedent of the conditional I want to derive, which is going to be FA arrow GA. Yes, I can assume that whole thing because that is the antecedent of the conditional I want to derive. But I'm not done, okay? Now what I needed to do, right, is derive the consequent of that conditional, right? And I noticed that the consequent of the conditional here of my target is also a conditional, right? So what I'm going to do then is actually start another subderivation in which, right, I get, oh yes, there, I just wrote that down as a subtarget and the marginalia there. Right, so what I'm going to do now is assume not GA because that's the antecedent, right, of the consequent of this whole consequent that I need to derive. Okay. All right. Now I need to derive not FA. Okay. I need to get not FA on the last line of this subderivation that I've started on line 2. Okay. Because that's what the rule requires. Now, how am I going to do that? Right? How am I going to do that? Well, let's see here. Yes, not FA. I already see some elements of a contradiction that I have in my assumptions. I got a GA right here, and I got a not GA right there. And that is a good indicator that I should use negation introduction, right? Because really, what this is right here is a negated formula. And so what I'm going to do then is I want to introduce a negation onto FA. So I shall assume, starting a third subderivation here, FA. All right. Now that's really helpful because FA helps me get GA from line 1. So I'm going to use line 1 and 3 to get GA using arrow elimination. Now I can grab line 2 and line 4, bring them together with conjunction introduction, create my contradiction as such, and then I'm done. Now I have satisfied this rule, and I can discharge the subderivation and put a negation on this assumption that I assumed for reductio. Right, so there we are. That comes from lines 3 through 5, and the rule that I use is negation introduction. Okay, so now I have derived the consequent that I wanted from this assumption in this subderivation here, and I assume this for conditional proof. So what I can do now is discharge that subderivation right here, move back to the left on line 7, and write not GA arrow FA. And that's what I ultimately wanted to derive in this subderivation here, right? So then I can write out the whole thing, right? And I derived it from no premises, right? That came from 1 through 7, arrow introduction. Right, line 7 came through 2 through 6. Right, let's see, you can kind of see that. Okay. Right, so that's how it's done, right? It's just a matter of working backwards from your target. There's no difference between this kind of thing and what we did in any of the other problems, all right? Now, where this gets a little tricky is it's not immediately obvious how you would work backwards from your target with something like this, right? This is called the law of excluded middle. This is a logical truth, right? So whenever you see something of the form like P or not P, in this case we have FA or not FA, that's the excluded middle, right? That's a logical truth, okay? Now, how do you go about doing something like this? Okay, there's no arrows we can work with here, so what do we do? Right, and the answer almost always is going to be the use of negation introduction. Okay, you're going to be assuming something for reductio, but you might be wondering, well, what on earth would I be assuming for reductio? This doesn't even make any sense. Okay, and I understand that. Okay, however, the answer is pretty simple. Right? We are supposing that our target is a logical truth. So the very opposite of our target then would be a logical falsehood. Right? And logical falsehoods are false in every model, just like contradictions are false in every model. So it's a sure bet that if we assume the negation of the excluded middle, and in this case it would be FA ring not FA. If we assume the negation of that, notice how there's a negation on the outside here, that's the main connective. You assume this whole thing for reductio. What we're going to end up doing is put a negation on this thing and then use the double negation trick at the end. So really, technically on the very last line, we're going to use negation elimination. However, right, this is going to be the strategy. Okay, so we have that on our slide here, And now what do we do? I mean, okay, great. How should we think of this? What can we even do with this? All right, there's an answer to that question. We need to treat this negation that we've assumed right here as one part of our contradiction. All right, let me just say that again. This is going to function as one part of our contradiction. All right, so what we need to do then is derive the other side, which is going to be FA ring, not FA. And you might be thinking, isn't that what we're trying to do ultimately? Yes, but we need to make some assumptions to be able to do that. Okay? So how on earth are we ever going to get the other half of the contradiction? There's actually a pretty simple answer to that. All right? This is what we need to get for the other part of the contradiction, right? As you notice here, one of the pieces inside of this thing is a negation, and not FA, right? And so you can actually assume the very opposite of that to put a negation on it, all right? And what we'll do then is introduce using ring introduction. Okay, ring introduction allows you to introduce things you need, right? Remember, this is the main connective here is a ring, and we don't have it anywhere, so we're gonna have to create it, and that's what we're gonna do. And so that's what we did with our assumption. Okay, that's what we did with our assumption. Okay, now you can use line 1 and line 3 to create a contradiction, right? That is a contradiction that has the form of P and not P. Okay, now you can put negation on what you assumed in line 2, which was FA, and so you're going to get not FA from lines 2 through 4 using negation introduction, and then you can do the same trick, right? On line 5 now, you can use the disjunction introduction rule again. Now you have the other part of the contradiction that you needed, right? You create the contradiction again, right? And now, right, you've derived a contradiction from this assumption, and so you can stop the subderivation on line 7, move back to the left, discharge everything, and write not FA ring, not FA, 1 through 7. Negation introduction, and then you use your negation elimination trick, and you're done. Okay, so the deal is here is that is pretty unintuitive. I understand this. Okay, that's unintuitive, and the reason why is because you're doing this contradiction disjunction introduction trick twice, but that's what you have to do in order to get to the end. Okay, and so what I recommend is that you try to do this on your own. Okay, just work the problem out on your own, and then come back to it and look and see how it's done. And I think you'll see why it makes sense. All right, you have to kind of do it yourself to see why it makes sense. It's hard to explain, right? The reason I'm wanting you to kind of dwell on this is because you will have to derive this problem or something that looks like this problem on the final exam. All right, so I want you to kind of have a good understanding of how this process works. All right, so we have practice problems here, right? These vary in difficulty. Okay, so this one here, you're going to be wanting to use arrow introduction all the way. And you're going to have to, start out by assuming the antecedent, right? And then derive the consequent, which makes you assume FA, right? You derive GA, then you get that, and then you get that, and then you're done. That's a nice, easy one. Okay, this one here, you need to use negation introduction. All right, so this is kind of something that we already kind of, it resembles something we just did, right? But you assume FA for negation introduction, right? You get GA, you derive the contradiction, you stop it, and then you're done. Now this one here, I believe this one is fairly challenging. Yes, this problem is like, what is it? It's 12, 13 lines long. I forget. Anyway, we can walk you through that, but I'm not going to go through this line by line here, but you can see how difficult some of this stuff can get, right? This gets complicated. So if you're up for a challenge, I recommend doing this problem, right? I recommend trying that, okay? Same thing with this one. This one's not easy as well. All right, so but do realize that all of this stuff can be done, right? I mean, you're given a premise here, that's true, right? But a lot of this stuff can be done just by kind of understanding the strategies of conditional proof and reductio ad absurdum. Right, so if you have questions, just shoot me an email or post a question on the page, the class page, or we can do a hangout session and talk more about it. Right, so I will talk to you later.